1 qubit gates, okay. 2 qubit gates, challenging. And especially the idea of entanglement. And now what? 3 qubit gates. Why do we need 3 qubit gates if we can entangle 2? Well, there's this thing called teleportation. Take the state of an unknown qubit, combine it with one of the entangled qubits, and transfer that state to a third qubit. And what we'll find is we'll be dealing with 8-dimensional vectors. Isn't that fun? And operators that are 8 by 8. So this should really test our linear algebra stuff and also see if our brain can hold on to it or our attention. Maybe you'll just say, way too much, I'm out of here. Ready or not, here we go. And here is the entangled pair. A is going to be the local qubit, and B can be anywhere. It can be far away if we want to. And what we want to do is try to teleport the state here over to the B state, which could be off-site anywhere far, far away. Let's look at this next step and see if that makes sense. You notice we've got this state, and this is the general state of any qubit. A alpha complex number times the basis state 0, and a beta complex number times the basis 1 state. And this is all the unknowns. That's what these U things are all about. Now, if you look at this, what does this look like? That is the Bell state broken down into this kind of stuff. And this entanglement that we just created, this is how that's represented. Now let's see if we can put this together. And this is the magic here. And I'll go over it in detail before this video is done. We go from this step down here to where here's the alphas, here's the betas, and here's the 3 qubits collection that represents an 8-dimensional column vector. Now we're going to apply a C0 gate. This C0 gate is what we did to do the original entangling, but now this entangling is going to be used only on the A. We're going to work with the unknown as the control bit. So if U is 1, then we flip A. Let's notice what happens here. U is 0, U is 0, no changes. U is 1, this bit flipped here, the A bit flipped. It's 1, so the A bit flipped. And the B is left alone. So after this C0 gate is applied, if we believe those rules, this is what we end up with. Compare this line with this line. First term is the same. Second term is the same. Third term is different. That's the bit flip. Fourth term is different. That's the bit flip. Now, to get everything performed correctly, we also have to do the Hadamard. And we're going to use the Hadamard gate on the unknown state. There's the results of the Hadamard gate. Notice this thing comes up to be a 1/2. How could that be a 1/2? Well, look at this statement here. Factor the 1 over square root of 2 from step 1 and the 1 over square root of 2 from H, the Hadamard gate. That gives us a total of 1/2. So here's our final state. Where did the teleportation come in? I don't see any teleportation. Here's the magic decoding bits. This is what retrieves the state from the B qubit, or Bob's qubit, if you want to talk about that. A was Alice, B is Bob.